Hi again for this presentation on transformations, mapping rotations on the coordinate plane. Going to walk you through three different examples of increasing difficulty. For the first example, a point rotation. The second example will be a polygon. Here I'll draw a triangle on the coordinate plane, rotated about the origin. And for the third example, a polygon rotation about the point xy, a floating point on the coordinate plane. For the first example, if I were to pose to you the question, what are the coordinates on point A 512 when rotated counterclockwise? A, 90 degrees, B, 180 degrees, or C, 270 degrees? Well, here I used Desmos, which is a free app that's very useful for high school teachers and students. And as you can see, I've plotted 512. And for this presentation, what I'm going to do is I'm going to take that point in coordinate one, in quadrant one, and rotate it on the map, as you can see here. The way I do this without making errors is I space out the point with a green rectangle. So as you can see, that forms a lower right triangle with base 5 and height 12. So in order to space out the rotation correctly, instead of using a circle, what I do is I rotate the rectangle so that instead of being upright, it's lying in quadrant 2. So now the base of the rectangle has a base of 12 and a height of 5. And the new location is still the diagonal from the origin because it's being rotated around. So the location after a 90-degree rotation will be at negative 12.5. This idea can be extended for another 90-degree turn by turning the rectangle block rotated about the origin. So as you can see, for a 180-degree rotation, that will move the point from quadrant 1 to quadrant 3. And for a 270-degree rotation, that will move the point from quadrant 3 to quadrant 4 as we go around counterclockwise like a carousel. So here I can accurately map each of the points without error just by using the diagonals of the rectangles that I'm rotating, pivoting around like a pinwheel around the origin. So the correct answers were negative 12.5, negative 5, negative 12, and 12, negative 5. For question number 2, triangle ABC has coordinates 5, 12, 3, 4, and 8, 7. What are the coordinates of triangle ABC when rotated 90 degrees, 180 degrees, and 270 degrees? Well, again, here on Desmos, I've graphed the triangle as a polygon ABC. And using this graphing tool, you can see the green triangle in the first quadrant. Again, I'm going to space out to point 3, 4 with that light blue rectangle, which I can rotate about the origin. But I'll also put a picture frame of a green triangle that contains the entire triangle. So you can see that the other points are along the perimeter of the larger frame. So the next thing I'll do is I'll rotate around the point 3, 4 around the origin using the same method as before, rotating the rectangle 90-degree turns from quadrant 1 into quadrant 2, into quadrant 3, and then to quadrant 4. For the next step, I'll do the same thing with the larger framed green rectangle. Again, rotating around the large rectangle 90 degrees, 180, and 270 degrees. This is a useful tool for spacing out the points precisely. And what I'll do next is I'll use the perimeter of the large rectangle to find the coordinates of the other 2 points of the triangle. Notice that 3, 4 is the diagonal of the smaller rectangles as framed. But what I'll do is in quadrant 1, I'm going all the way to the top, going 5 boxes to the right, and that's the point 512. Continue along to that opposite corner and go down 5 units, and we're at the point 87. Well, since we've rotated the entire green rectangle 90 degrees, I'm spacing out again from the corner along the axis. So now I'm at negative 12, 0. I have to walk up 5 units, and the new coordinate is negative 12, 5. Continue to the opposite corner, make a right turn, and go 5 units, and you find the third point of the triangle at negative 7, 8. Then I can connect the dots, as you can see with those gold stars that I placed, and I have the precise lattice points for that triangle rotated perfectly 90 degrees. Similarly, I can continue with this idea by blocking off the other vertices of the triangles, not only in quadrant 2, but also in quadrant 3 and in quadrant 4. As you can see here, the blue arrows, again, are attached to the axis as if the axis is being rotated. So for the 180-degree turn, instead of going up 12 units, I go down 12 units, make a right turn 5 steps, place a gold star, go to the corner, make a right turn, go 5 steps, and then place a gold star for the third vertex of the triangle. With this method, you can precisely place the lattice points for the triangles very quickly, whether it's a 90-degree problem, 180, or 270. And you can see the polygons as shown with the precise locations of the new lattice points, whether it's a 90-degree, 180-degree, or 270-degree rotation from the original triangle that was in quadrant 1. Notice once again, as you master this, that a 90-degree turn is a rotation from one quadrant to the next one as we carousel around counterclockwise. So since the original shape was in quadrant 1, the pre-image, the image will be in quadrant 2. Similarly, for 180 degrees, well, that's 2 90s. So we've moved from quadrant 1 to quadrant 3. And for 270 degrees, we've moved 3 quadrants down to quadrant 4. For the last and most difficult problem, sometimes you're given a problem where there's a polygon such as triangle ABC, but we're rotating around a floating point on the map. So here, triangle ABC has the same coordinates, 5, 12, 3, 4, and 8, 7. But what will be the new coordinates when rotated about the point 10, 14 on the map? 90 degrees, 180 degrees, and 270 degrees. Well, the skill here, as you can see, I have the same triangle mapped, but I'm focusing only on quadrant 1 because the point 10, 14 is above the triangle and to the right. What you do is you use that point as a point of origin. So again, I'm spacing that green starting block as the distance to the point of rotation. Then, since that's the new point of rotation, I'll now anchor that block going around 90 degrees, 180 and 270. And then I'll also make a larger blue rectangle that spaces out the, oh, here it is properly. This blue rectangle also rotates 90 degrees, 180 and 270 degrees. So this double pinwheel is how we're going to rotate all 3 vertices of the triangle around the new point of focus, 10, 14. So since each distance is relative to the point 10, 14, again, I'm just using the rectangles, and since I've used it to contain the triangle, I can use the long diagonals of the small rectangle to place the new points, and also of the large blue 7 by 10 rectangle, I can use those long diagonals to place the second vertex of each triangle. For the third vertex, which is floating inside that blue frame, again, I'll use the axes, y equals 10 and x equals 14 and spacing out 7 boxes along the perimeter. So you have to make a right turn and then go into the blue frame here. So we go down 7 and then 2 to the right. So if we rotate it 90 degrees, now we have to go 7 units to the right and then 2 units down so that it's mapped in the same proportion, and we keep the isometry. Similarly, for the 180 degree rotation, we'd go 7 units up and 2 to the right to place the third vertex. And for the 270 degree turn, 7 units to the left and 2 units up. I've highlighted the 0.87 that's being rotated and the images for 90, 180, and 270 in the red squares. Since they're properly spaced on the lattice point, we now have the triangle rotation using these 2 rectangles. We use the 2x5 rectangle for that point closest to the point of rotation. And then we use the 7x10 rectangle for the point that's furthest away from the point of rotation, 1014. So now we have 2 points of the triangle perfectly matched with these 90, 180, and 270 degree turns. Lastly, we use the polygon function to make sure that we set we type in the coordinates correctly for each lattice point, and lo and behold, we have each triangle rotated 90, 180, and 270 degrees properly around the point 1014. I hope that this video was useful to you in your preparation for your upcoming SAT exam. Thanks for having me, and thanks for watching my video tonight.